Introduction. The operating cycle of an IC engine can be broken down into a sequence of separate processes: intake, compression, combustion, expansion, and exhaust. Actual IC engine does not operate on ideal thermodynamic cycle that are operated on open cycle. The accurate analysis of IC engine process is very complicated. To understand it well, it is advantageous to analyze the performance of an idealized closed cycle. Before going to this cycle, the student might be already studied in the IC engine the keywords like swept volume, clearance volume, top dead center, bottom dead center, compression ratio, clearance ratio. Such things already you might have studied in the previous semester. That thing you might remember in your mind while going to discuss this session. Okay, next, assumption of air standard cycle. The Otto cycle basically working on assumed to be a air standard cycle because the assumptions are the working fluid throughout the cycle is only air. The engine should be frictionless throughout the cycle. The value of Cp and Cv to be constant throughout the cycle. Next point, the air acts as an ideal gas. Combustion process are replaced by well-defined heat addition process. The exhaust process is replaced by a heat rejection process. Difference between actual cycle and air standard cycle. We know in air standard cycle, air is assumed to be used as a working fluid, but in actual cycle, the mixture of air and petrol is used as a working fluid. So, we should know about the difference between actual cycle and ideal cycle. These are all some key points. Air standard cycle differs from the actual by the following. The gas mixtures in the cylinder is treated as air for the entire cycle, and the property values of air are used in the analysis. The real open cycle is changed into a closed cycle by assuming that the gases being exhausted are fed back into the intake system. Okay, Otto cycle. Now we are going to the content. Otto cycle. Otto cycle is the ideal cycle for the spark ignition engine, which is named in honor of the German engineer named Nicholas Otto, who made a very big contribution to the evaluation of the internal combustion engine. Also, this cycle is known as constant volume cycle or SI engine cycle. And applications. Nowadays, petrol engines and gasoline engines are working based on this cycle. Examples: car, jeep, bikes, etc. Otto cycle. Now let me discuss about the PV and TS diagram of Otto cycle. The figure shows the pressure, volume and temperature entropy diagram of an Otto cycle. Crusher move
புரியல
crusher move பண்ணால சொல்லி கொடுக்குறப்ப
மோஸ்ட் மூவ் பண்ணலாம் சார்.
Okay, now let me discuss about PV and TS diagram of Otto cycle. This is pressure volume diagram of an Otto cycle engine. Here there are four processes. Process 1 to 2 is isentropic compression, and 2 to 3 constant volume heat addition, and 3 to 4 isentropic expansion, and 4 to 1 constant volume heat rejection. These are all the four processes involved in this Otto cycle. In the first process, the air fuel mixture is isentropically compressed from this point 1 to point 2. So compression takes place. So here the point 1, the value of volume V1 and pressure P1, and at point 2 the value of volume V2 and pressure P2. In this process, the pressure increases from P1 to P2 and the volume decreases from V1 to V2. This is the isentropic compression process. Here, next process 2 to 3 is a constant volume heat addition. In this process, the volume is constant, V2 equal to V3. In constant volume, heat is supplied in this process. So temperature and pressure gets increased from 2 to 3. Temperature and pressure gets increased from 0.2 to 0.3. Here pressure increase from 2 to 3. Here temperature increases from 2 to 3. And process 3 to 4 is a isentropic expansion process. In this process, the burnt fuel is expanded, so to do the work output. In this process, the pressure decreases from P3 to P4, and also the temperature decreases from 3 to 4. The next last process 4 to 1 is a constant volume heat rejection. In this process, heat exhaust gas are sent out. The heat is rejected. 4 to 1. In this process, temperature further decreased from 4 to 1 and pressure also come back to the initial point. This is the PV and TS diagram of Otto cycle. In this TS diagram, the temperature is plotted in the y-axis and the entropy is plotted in the x-axis. Here in the process 1 to 2, compression process, the temperature gets increased from 0.1 to 0.2, and process 2 to 3, but the entropy remains constant, S1 equal to S2. In this process 1 to 2, entropy remains constant, S1 equal to S2. In process 2 to 3, heat input, so the temperature gets increased from the 0.2 to from 0.3. And 3 to 4 is a isentropic expansion process. So here the entropy constant, S3 equal to S4, and the work output is obtained. And 0.4 to 1 is a constant volume heat rejection process. These are the what is going in this cycle. Okay. We discussed previously in the diagram, Otto cycle is a 4-process cycle wherein it is composed of 2 isometric process, isometric or constant volume process, and 2 isentropic process, constant entropy process. These processes are followed. This diagram already we have shown. In order for us to easily understand the concept of those 4 processes, we need to make ourselves be familiar of the PV, pressure volume, and TS, temperature versus entropy diagram for this type of cycle, which is shown in the picture above. For better understanding of this cycle, we should familiar with the PV and TS diagram of the Otto cycle. Here, the same diagram here, but here the RK, that is compression ratio. Compression ratio means the volume of compression before compression to after compression in a IC engine cylinder. Volume of fuel before compression to after compression in the IC engine cylinder. That is the ratio of fuel before compression, ratio of volume of fuel before compression to after compression. Here V1 is the total volume and V2 is the clearance volume of the cylinder. We assume like that V1 is the total volume and here V2 is the clearance volume. So from that compression ratio Rk equal to this V1 divided by V2. V1 equal to here V4. So we substitute instead of V1 equal to V4 and V2 equal to V3. So the compression ratio Rk equal to V4 by V3. In this process, compression ratio and expansion ratio both are same. See the PV diagram. This diagram, compression ratio 1 to 2 and 3 to 4 are parallel and equal. So in this Otto cycle, compression ratio and expansion ratios are to be same. And one more thing, the PV diagram and TS diagram. The TS diagram is the mirror image of this PV diagram in this Otto cycle. Next, pressure, volume and temperature relations. You know the pressure, volume and temperature relations. P1 V1 power K equal to P2 V2 power K at S1 equal to S2. Entropy constant, when entropy is constant, P1 V1 K equal to P2 V2 K. From that we can find out the pressure P2 equal to P1 of V1 by V2 the power K. P2 equal to P1 into V1 by V2, we know compression ratio Rk power K. In the process 2 to 3, is a isometric addition of heat. This process is also known as the power stroke, wherein the spark plug of the engine ignites the compressed mixture of air and fuel. The process is mathematically proven with these following relations. Here, pressure P, volume V and temperature T relations, PVT relations. Here, we know the basic equation P1 V1 divided by T1 equal to P2 V2 divided by T2. Like that, the process is initiated from point 2 to 3. So P2 V2 divided by T2 equal to P2 V2 P3 V3 divided by T3. Like that, when we work out, the volume is constant, so volume cancelled. We get the relations T3 by T2 equal to P3 by P2. From that we can find out the T3, temperature T3 equal to T2 into P3 by P2. This is the pressure ratio. P3 by P2 is the pressure ratio of this cycle. T3 is the peak temperature of the cycle. Maximum temperature or peak temperature of the cycle is T3. Okay, next one is heat addition QA. If you know the formula, heat addition QA equal to mass into CV, specific heat at constant volume into temperature difference in that particular process. The heat addition takes place the process 2 to 3. So the temperature difference between the process 2 to 3 is higher temperature T3 and lower temperature T2. So T3 minus T2. Heat addition equal to mass of the fuel into calorific value of the fuel into delta T, temperature difference on that particular process. Similarly, the process 3 to 4 is a isentropic expansion process. That process is mathematically proven with the following relations. So this process T4 by T3 equal to V3 by V4 K minus 1 at entropy constant. So this is the inversion of the compression ratio. V4 by V3 equal to Rk. So this is the inversion. T4 by T3 equal to 1 by Rk power K minus 1 or Rk equal to V1 by V2, that is equal to V4 by V3. and P4 into V4 power k equal to P3 into V3 power k, P4 equal to P3 into V3 by V4 power k. Next one is heat rejection. Heat rejection QR equal to M into CV into T1 minus T4. Heat rejection takes place in the process 4 to 1. So mass of the fuel into calorific value of fuel into delta T, temperature difference during that particular process 1 to 4. Work done. Now here are the other parameters necessary in validating the performance of the Otto cycle. So net work done for analyze the efficiency of the Otto cycle, we must need the work done of that particular cycle. Work done W net equal to heat applied minus heat rejected. We know efficiency equal to net work done divided by heat supplied. Net work done equal to heat supplied minus heat rejected divided by heat supplied. So we are solving this equation. Finally we got 1 minus QR by QA. And we have to convert this relation in terms of compression ratio. Efficiency equal to 1 minus 1 by Rk power k minus 1. This is the final efficiency equation to find out the efficiency of the Otto cycle. Because based on the compression ratio, it is easy to find out the efficiency. But in case of the temperature inside the IC engine, we can find out very difficult at a particular process because the fraction of second, so many cycles going inside the engine. So we have to change this equation in terms of compression ratio of the engine. So finally we got efficiency equal to 1 minus 1 by Rk power k minus 1. Based on this efficiency equation, we conclude that if we increase the compression ratio of the engine at a certain level, for example 5, 6, 7, up to 6 or 7, the efficiency keeps on increase when increasing the compression ratio. After that, it keeps on decreasing. Next one is mean effective pressure. Mean effective pressure means the formula for that mean effective pressure means net work done divided by stroke volume V1 minus V2. This is stroke. V1 to V2 is the engine stroke, movement of piston. Stroke means movement of pistons from bottom dead center to top dead center. So we consider here the bottom dead center and the top dead center in an engine. The stroke is V1 minus V2. So mean effective pressure equal to W net by V1 minus V2. Problem solving. This is some example problem is there. Before going to solve the problem, we should clearly understand the cycle, how the PV and TS diagram are in the Otto cycle, what is going to happen in this cycle. Such a thing the student must remember. Based on this concept and formula, the student will be able to solve the problem easily. Otherwise it is difficult while mugging. Let us now solve a problem relating to the ideal Otto cycle. An ideal Otto engine, this is the problem, an ideal Otto engine operating on the hot air standard with K equal to 1.34 as a compression ratio of 5. At the beginning of the compression, the volume is 6 feet cube. The pressure is 13.75 psa and the temperature is 100 degree Fahrenheit. During the constant volume heating, 340 BTU British thermal unit are added per cycle. Find the following. Clearance C, the temperature at the end of the isometric addition of heat, or the temperature at the beginning of isentropic expansion T3. Pressure at the end of isometric addition of heat, or the pressure at the beginning of the isentropic expansion P3, and cycle efficiency and the mean effective pressure. These things we have to find out in this problem. So first of all, before going to solve the problem, we should read the problem 1 or 2 times so that we can understand what are the parameters are given, what units are in the parameter. Such thing we should understand first before going to the problem. Problem solving. In solving for this review problem, we students or engineers need to know and master the 3 C's of mechanical engineering, namely the concept, constants and conversions. So we will now start computing for what is asked for this sample problem. This is the important thing, 3 C's of mechanical engineering. First one is concept and constants and conversions. In this problem, we know the formula for compression ratio RK equal to 1 plus C by C. So, while cross multiplying this equation, C into RK equal to 1 plus C. C of RK minus C equal to 1. So here C, commonly C takes out. So C of RK minus 1 equal to 1. From that, as clearance C equal to 1 by RK minus 1, that is equal to 1 by RK. Compression ratio in this problem given as 5. 1 by 5 minus 1 equal to 1 by 4. That is equal to C equal to 0.25, in percentage 25%. We arrived with a clearance of 0.25 or 25% based on this equation and this equation conversions. Temperature at the end of isometric addition of heat, or the temperature at the beginning of isometric expansion. In obtaining the temperature at the beginning of the isotropic expansion or at the end of the isometric addition of heat process T3, the first thing to do is to obtain the temperature at the beginning of the isometric addition of heat process, which is T2, using the temperature relations T1 and T2, deriving the formula so that it now appears to be looking for T2 and then substituting the data we had. This is the relation for that particular process. T2 by T1 equal to V1 by V2 power K minus 1. We know V1 by V2 is the compression ratio. So instead of V1 by V2, we put it as RK power K minus 1. From that, T2 equal to T1 of RK power K minus 1. T2 equal to T1 is 100 given in the problem, and RK is T1 is 100 plus 460 into RK is 5, K is 1.34 and 1. So by solving this equation, we get 508 degree Fahrenheit. We arrived with the temperature of 968 degrees Rankine, say 968 degree of Rankine. We have to convert this Rankine temperature into Fahrenheit. Next one is mass of the air. Next thing, to obtain the mass of the air Ma, which can be obtained by using the universal gas constant formula and by using the data provided for the start of isentropic compression process. You know the characteristic gas equation PV equal to m of T. From that we can able to find m equal to PV by RT by substituting this value pressure, volume and R and temperature value. We get mass as 0.398 pounds. Next one is CV. The value of CV equal to R by K minus 1. Substituting this value, we got CV equal to approximately equal to 156.88 feet pound per minute per unit LBM per unit degree Rankine. Finally, since we now have the mass of the air Ma, the specific heat capacity of the air at constant volume and at K of 1.34 CV and the temperature at the beginning of isometric addition of heat process T2, and since we are provided with 340 BTU of energy at the heat addition process, we can now obtain the temperature at the end of the isometric addition of heat process by using the formula for calculating QA and deriving it so that it appears that it is looking for T3. The solution goes for like this. QA, heat obtained equal to mass into CV into T3 minus T2. From that, modifying this equation, T3 equal to QA by M into CV plus T2. Substituting all those values in this equation, finally we got the T3 temperature or peak temperature T3 equal to 4750 degree Fahrenheit. Next, by using this relation, pressure volume relation, P2 V2 K equal to P1 V1 K. From that relation, we find out the value of P2 equal to 118.83 PSA. Pressure at the end of isometric addition of heat or the pressure at the beginning of isentropic expansion P3. In order to obtain the pressure at the beginning of isentropic expansion, the first thing to do is to obtain the pressure at the start of the isometric addition of heat process, which is P2, and this can be obtained by using the pressure and volume relations during the isentropic compression process. The solution goes like this. By using this pressure temperature relation, we are able to find out the peak temperature P3. P3 equal to P2 of T3 by T2. By substituting these values, finally we arrived P3 equal to 639.6 PSI. Cycle efficiency. Since we are provided with the compression ratio of the ideal Otto engine, we can directly obtain the efficiency by using the formula wherein compression ratio RK is mainly used. The solution goes like this. This is the efficiency formula for the Otto cycle. E equal to 1 minus 1 by RK of K minus 1. We got compression ratio 5 in this problem and K value. Directly substituting these values in this equation, finally we arrived efficiency of this Otto cycle engine as 42.14%. Thus we obtained a cycle efficiency of 42.14%. Next one is the mean effective pressure. In solving for the mean effective pressure of the ideal Otto engine, we need to obtain the net work done by the engine and since we are provided with the heat added during the isometric addition of heat process, and at the same time we have computed the cycle efficiency previously, we directly obtained the net work done by the ideal Otto engine by using the formula and equating it so that it appears that it looks for the net work done. The solution goes like this: efficiency equal to net work done divided by heat applied. From that equation, net work done equal to efficiency into heat applied. Net work done equal to efficiency we have arrived as 42%. So substitute these values and finally we got net work done equal to 143.28 BTU. So by now we are a step closer in obtaining the mean effective, which can be obtained by utilizing the formula as found below, and since we hadn't obtained the value of the volume at the end of the isentropic compression V2, we can obtain it by using the formula for the compression ratio RK, so that we can obtain V2, and the solution goes like this: RK equal to compression ratio RK equal to V1 by V2. From modifying this equation, V2 equal to V1 by RK. So substituting these values, we receive that V2 clearance volume V2 equal to 1.2 feet cube, and we are able to obtain the volume of 1.2 ft cube, and substituting the data we can now obtain the mean effective pressure, and the solution goes like this. You know, mean effective pressure equal to net work done divided by stroke volume or swept volume. We find out these values in the previous steps, V1 and V2. W net also we have find out. Substituting these values in this equation, we got mean effective pressure as 161.3 psia. Conclusion: before I end this article regarding Otto cycle, I would like to advise mechanical engineering students to not memorize the formula. The key to mastering the Otto cycle is through mastering the concept by way of familiarizing the PV and DS diagram of the Otto cycle and mastering the fundamentals of thermodynamics. I guess that would be all. Thank you.